Can you see the screen now?
Yes, sir.
Yes, sir.
So this topic is in continuation of the previous design of the foundation system where we are designing the isolated footing. Combined footing is basically the footing which is built by combining the 2 or 3 columns together into a single footing. So basically when it is needed, when the single isolated footing is insufficient or when the area is overlapping, when the columns are too closer to each other and the possibility of the isolated footing doesn't exist, then we have to go for the combined footing. Combined footing resting on the 2 columns behaves as a longitudinal beam along the length of the footing. Resting on the column assumed to extend along the full width of the footing. So combined footing is basically for the 2 columns, and we design it as a in the 2 direction. One is the longitudinal direction and also in the transverse direction. Mainly the load is carried out in the longitudinal direction, but there is a strip which is also taking some part of the load. The strip is also extended in the transverse direction. As you can see in this figure, the combined footing is made by the 2 columns. If we have we try to make the resultant in such a way that the resultant of all the forces, which is the sum of the load acting on the column 1 P1 and the load acting on the column 2 as P2, should be equal to R, and the resultant is passing through the centroid. So we have to set the dimensions depending upon the available given conditions at the site, that how much footing can be extended beyond the columns on the one end on the other end, and then we can provide the more projection on the other side of the column if there are restrictions on the one side. So we set the dimension in such a way that we determine the location of the resultant, and then the location of the resultant must be passing through the centroid of the footing. It means that if the footing length is length L, then the resultant must pass through the L by 2. Similarly, in the transverse direction, we mainly provide the more amount of the steel in the transverse strips, which are shown in the figure. C1 plus D is the width of the transverse strips. So here the larger amount of the steel is there because mainly in the transverse direction the bending is mainly the bending is produced in this region, and in the other region we can go with the nominal steel. Important point is that the centroid of the combined footing must coincide with the location of the resultant load on the footing. So how it is possible? This makes the resultant moment of the footing transfer to the soil equal to 0, which produce uniform pressure under the footing and avoids the tilting of the foundations. You know that when I am applying the force on some area and I pass the centroid through the centroid, then it means that there is no unbalancing movement. When there is no unbalancing movement transferred to the soil, there is a uniform pressure under the footing. So reason for that is the uniform pressure development under the footing. So that's why we take the sum of the moments of the resultant and sum of the moments of its components should be equal as per the Varignon theorem. So depending upon the clearance is available, the footing is to be extended beyond the edge of the column near the boundary. This makes the footing safer against the punching shear and help in economizing the depth of the footing. We can try the extend the footing beyond the column on all sides. If the space is not available, then it is not possible. But if it is available, so that the larger punching perimeter can be obtained and we can avoid the punching shear. The distance between the shorter edge of the footing towards the column closer to the boundary and the resultant of the load is evaluated. The footing is longitudinally extended on the other side of the resultant of the load by the same distance. So first of all, the point is that locate the resultant from the one side of the footing, and then the footing provide the similar length after location of the resultant. Let's say the resultant is obtained at some distance x, so we will multiply that x with 2 and that will be the length of the footing. The required area of the footing is also very simple. The length is determined from that expression, and the area of the footing is the similar, the total load divided by the allowable bearing capacity. So in this way you can obtain the width also, because the length is determined from the force from the Varignon theorem application, and by the analogy of making the resultant passing through the centroid, and the width is determined by the area required divided by length, because area is B into L. So what is the area required? The area required will be the total service load for the one column, for the two columns, or even more than two columns, divided by the allowable net bearing capacity. So then you decide the thickness of the footing, and then you compute the shear force and the bending moment and design the footing. The depth is first computed from the one-way shear criteria. The depth is then checked for the punching shear criteria, and we can reduce the live load, but no need to take the pattern loading, because pattern loading is adopted for getting the critical moment and the shear in the foundations, and no need to apply the pattern loading in the footing, because ultimately this is normally a smaller part of the total load for the concrete structure, and effect of the pattern load is normally finish till reaching the footing level. So pattern loading is not taken, but you can reduce the live load in case of the footing design. The reason is that normally the building is not fully loaded all the time, so you can reduce the 20% live load reduction factor in case of the foundation design. So a longitudinal section of the footing is considered first of all, and the columns are considered as the supports. The longitudinal section of the footing behaves like a beam, because it is an inverted type of the beam where UDL is acting upward and the column load is acting downward. This slide shows the behavior of the footing. The column, between the column there is a tension at the top side. It is opposite to the conventional beam, because in the foundation the pressure is acting upwards. So if the column distance is large between the column, then there is a tension between the columns, and under the column there is a sagging behavior, and between the column there is a hogging behavior. So tension is at the bottom side under the column load. Tension is at the top between the two columns. But if the columns are very closer to each other, then even it is possible that throughout the top tension is developed. Throughout at the top, the tension is developed. The reason is that the overhang length beyond the columns is too small, that there is no possibility of developing some tension in the bottom, and as a whole the footing is totally showing the hogging behavior throughout the length. So it means that the larger top steel will be required for the foundations, and under the column normally the bottom steel is needed, and between the column mid span the top steel is needed in the along the length, whereas along the width the bandwidth are bended just like isolated footing, so tension is produced at the bottom side. So in case of the transverse direction, the bottom steel is needed along the B. The load acting on the footing is equal to the width of the footing multiplied with the net contact pressure. So pressure multiplied by the width gives you the UDL actually, because when you are designing the longitudinal direction of the footing, you need a UDL. So how to get the UDL? Pressure multiplied by the smaller dimension, so width of the footing. So then you can design it along the length. The shear and the bending moment are plotted and critical shear is determined. Point of inflection, point of zero shear is determined. Point of maximum negative moment is determined. Point of maximum positive moment, and then you can design the foundation for the flexure. Apply the shear check and then design the foundation. You can consider the column load as a point load normally, but in some cases when the column size exceed 2-3 feet, then I think it is better to take it the real scenario. The real scenario is that the column is acting throughout its width. So you can consider that load as a UDL load. So sometime the column load is considered as a point load and sometime it is considered as a UDL load. Transverse bending moment is also computed in the transverse bandwidth and that is similar to the isolated footing procedure, and the upward tension is developed under the bottom due to the upward loading in the transverse strip. Now the length of the footing is calculated by using the Varignon's theorem that the moment produced by the resultant of forces should be equal to the sum of the moment produced by its components about the same point. So the equation becomes R into X into P1 X1 plus P2 X2 and so on. You can determine the from that you can determine the X value, the location of the resultant, because all the point load and the moment arm is known, and from that we can locate the resultant. The resultant location can be found and resultant must pass through the centroid of the footing. In this way, uniform pressure will be developed under the footing. Let's say if there are two columns and you want to find out the location of the resultant as X bar. So the first type of the of this is let's say this is the case. There are two columns. Now you can take select any point about which you can take the moment. It can be left edge of the footing or right edge of the footing, which is known. Let's say we know about the distance on the left side, or our column is at the boundary, or we can only, so we can take the moment at any known point. So normally the column center, one column center point is known. So we can take the moment at the left column P1 where the P1 is acting. Center, we can take the moment at the center. So what will be the moment at the column center for the resultant? Resultant moment will be R into X bar. And what is the moment of all other forces? So all other forces are P1 and P2. But because I am taking the moment at the P1 location where the P1 is passing, so the moment of the P1 becomes 0 and the moment of the P2 will be P2 into S about the same point. So as per the Varignon theorem, R into X bar should be equal to the P2 into S. So this means that X bar should be equal to P2 into S divided by resultant, where resultant is P1 plus P2. So this will give the location of resultant X bar equal to P2 into S divided by P1 plus P2. But this formula is valid when there are two columns and you are taking the moment at the centroid of the one column. So X1 is the distance between the column center and edge of the footing. You can see here X1. Now it means that our resultant is passing the location of the resultant, basically L by 2 is what? L by 2 is X bar plus X1. L by 2 is X bar plus L X1. So it means that the length should be equal to 2 times X bar plus X1. This is a simple analogy. You can determine the length from this expression. Then your resultant will pass. If you compute the length from this analogy, that you locate the X bar and add the any overhang distance, whatever is available, which is from the center of the column to the edge of the footing. So X bar plus X1 is basically L by 2. It means that the length of the footing is 2 times the X bar plus X1. So in this way, the length is located and you then compute the area of footing required, and that is equal to the load over net allowable Qn, net allowable bearing capacity, and when you decide the load over net allowable bearing capacity, we multiply it by the length, so you can determine the B value. So area is basically L into B is R over Qn, but when the L is already known, you can easily compute the B value. So all these dimensions are first the length by 2 is determined, then length is determined, then B is determined. Point is that not all the time the combined footing is the rectangular footing like shown in the figure. Sometime it is like trapezoidal figure, sometime it is a polygon type of figure, sometime it is a two rectangular type of footing. So here the different footings are shown in the figure C, D and E. Finally, this is important that the centroid of the footing the resultant must be passing through the centroid of the footing. And second thing is that under the larger load, you should have the wider area. Under the smaller load, you can have the lesser area. So in this way, you can make a different design of the footing. Whatever is the design of the raft of the combined footing, the important point is that you get the UDL under the footing. So how to get the UDL when you are resultant of when you know the centroid of the footing and try to pass the resultant through the centroid of the footing. So you have to adjust all these dimensions L1, L2, B1, B2. You can simply adjust these dimensions. Once the location of the resultant is known, then all the dimension can easily be adjusted. How? You know that what is x bar plus x1 because location of the resultant is computed from the Varignon theorem. This gives you the L1. Now your L1 and the area which is bounded by L1 and B1 zone, the same area should be bounded by L2 and B2 zone in this case. And in the E figure, the area bounded by L3 by the centroid till the centroid of the point to the should be equal to the area on the right end of the centroid and the left hand side of the centroid. Then you will get the uniform pressure. So you can adjust these dimensions so that finally the resultant should be passing through the centroid of the footing. Even in case of the multi-column footing, which is more than two column, normally I say it as a multi-column because it is a 3 columns or 4 columns or even 5 columns. You can provide this type of footing and the same procedure is followed. You first determine the location of the resultant, then you determine the length of the footing and width of the footing and so on. The plan and the sections are shown. Sometime with more number of column, we can connect the to eliminate the punching shear effect. We can if the thickness of the footing comes out to be very large, let's say your combined footing you want to design, but the thickness is coming as 4 feet 1 point something meter. So rather than making a throughout the thick raft, you can provide the larger beam in the column line and you can reduce the pad thickness other than the beam zone, and even the punching shear is also eliminated and the transverse bending will also be reduced and all the longitudinal bending will be shifted to the beam. So this is another type of the footing. This is called as the multi-column footing with footing beam, and practically we have designed many footing in this way. In Pakistan also lot of footings are there. Multi-column footing with footing beam is not a common footing, not available in all the books, but we have been trying, and even Dr. Zaid Siddiqui was also designing. So we were always trying because sometimes the problem with this footing is the making the balancing of the forces. So there is all the time unbalancing movement is obtained at the center, but we should set the dimensions in such a way that resultant should pass through the centroid. But sometimes it is not possible practically, so then the imbalancing movement is produced in the middle. But with this type of footing, we can control the imbalancing movement by providing the excessive reinforcement. This was all about the lecture. If you have any question, you can ask related to the foundation design, combined foundation design. Next, we are starting with the problem of the combined footing.
सर फिगर डी और ई में हम B1 और B2 को कैसे फाइंड करेंगे?
आप यानी कि B निकाल लेंगे ना कि एवरेज B क्या चाहिए. अगर इफ यू आर गोइंग फॉर रेक्टेंगुलर फुटिंग, you can compute the B, and then you have to select the B1 and B2 in such a way that the area bounded by the B1, okay, and this L1 zone, जो L1 B1 trapezoidal बन रही है left end of the centroid, that area should be equal to the area L2 B2, which is bounded by the right end of the centroid. So if these two areas are same, then it means that you are having the ideal case because your resultant is passing through the centroid then. So it means that B2 is lesser to have the equal area of B1 and L1 zone for the right hand side also. You need a larger L2. So L2 will be more, B2 will be less. At the similar time, B1 will be more than B2, larger, and L1 will be lesser than L2. So it is possible, but you have to compute the areas bounded by the L1 B1 region and L2 B2 region. And you have to play with the, you can say, geometrical dimensions for setting the foundations in such a way that resultant should pass through the centroid.
सर कॉलम को हम यूनिफॉर्म लें या पॉइंट लोड लें, इससे आंसर पे कितना फर्क पड़ सकता है सर?
माइनर फर्क पड़ता है, यू कैन से कि मेजर नहीं है. When the column sizes are nominal, like smaller sizes, but if the column is, we have seen that when the column side exceed about 500 millimeter, then it's better to take it as a UDL. It also depends upon the spacing between the column, that for the total length of the footing, how much is column is getting the place, how much percentage column is basically located for the total length or the width of the footing. So if you feel that reasonable width of the column is there, and then ideally speaking, I mean, going taking it UDL is a better option.